second speaker today is Reese Hodson, again from Infineon Technologies in Bristol, where he is a senior verification engineer. The title of his talk is ADAS IP Case Study, Decoupled Generation and Simulation for Functional Verification. So it's an application of what Tim has just introduced for us. Whilst working on Infineon's portfolio of ADAS IP, Reese is focused on improving the efficiency of the verification workflow using the latest industry ideas as well as homegrown machine learning techniques. Over to you, please, Reese. Thank you.
Thanks, Mike. Yeah, as Mike mentioned there, this presentation really is sort of a follow-on of what Tim has just presented, where I kind of pick out a few of the benefits that sort of Tim has mentioned and maybe do a bit more deep diving into those and fleshing them out with respect to the IP that I work on for Infineon, which is the ADAS IP. So in the ADAS IP team, we've sort of embraced this decoupled approach over the past sort of 3 to 4 years. So I'll go into a bit of the background and why we decided to move to this approach. Tim's already sort of touched on this, and then I'll go into our kind of generation test bench and simulation test bench, kind of sort of a brief overview of those two and why we took some of the choices in those architectures, and then some of the benefits that we've seen and some enhancements as well that we would like to make in the future. So to start with, we in the first generation of our ADAS IP, we had a kind of a traditional coupled generation and simulation environment, which was written in SpecMini. So SpecMini was definitely the previously kind of the preferred verification language at Infineon. We had quite a lot of common reasonable verification sort of components already written in this language, so it was a natural choice at the time to write the test bench in this language. So yeah, as I mentioned, it was a coupled environment. However, the ADAS IP that we were working on is highly configurable. So you know, around 300 to 400 configurable fields, and there's a large amount of sort of interdependency between those fields. So you can imagine there'd be quite a lot of constraints to write, which there are, and those constraints were sort of constantly evolving as the maturity increased, and that, as Tim mentioned, it changed sort of the behavior of the test cases that we were running. As soon as we would sort of modify a few constraints, a different configuration would be generated, and our test cases no longer hit the same coverage. So it was decided to make some enhancements during sort of the process of the closing coverage on the first generation and also for the second generation. So during the first generation, we introduced replay mode, which was essentially what Tim was talking about in that previous presentation, whereby we would generate configuration and store that test case off, and that test case would be allowed the decoupled simulation environment would be able to read in that test case and reproduce the same behavior. And then this was followed by more kind of decoupling, more placing more of the randomization in the simulation environment over to a generation environment, and also completely changing the language of the simulation environment from E to system Verilog. And I'll talk a bit about sort of the benefits of using the two languages that we use. So this is sort of the same data that Tim showed in his slides regarding the coverage closure that we kind of saw. It's just a bit of evidence of how the decoupled approach can help with random instability, really. So yeah, so Tim touched on this, so I'll probably just breeze past this bit. So yeah, our generation test bench is, as I said, is written in SpecMini, and it's able to, well, it essentially has two modes. So you can use you can make your generation test bench produce a random configuration, or it can read in some kind of pre-generated test case, which can be in a variety of formats: XML, text. So long as you write the supporting code for that in E, you can choose whatever sort of format you want for these pre-generated tests. So your generation environment can optionally read in these pre-generated tests as kind of extra constraints to layer on top of the core constraints, and it will spit out for you a full configuration, some stimulus like triggering, for example, for your design, and if you have a DUT model integrated into your generation test bench, you can also at this point output something like expected data, for example, like a memory view that you expect at the end of your test case. And what we do is we bundle up all these files in a zip file, and this is kind of the what we would sort of maybe refer to as sort of your portable tests that you're able to sort of port horizontally and port vertically, as was asked in that kind of previous question. So it's a mixture of file formats depending on what makes sense for your team and for your design. And then at the bottom here we have the simulation test bench, which is written in System Verilog, which is sort of nothing different to what you expect apart from this this first box where it's able to read in your configuration and stimulus and expected data, and yeah, then it contains your normal kind of functional models and checkers, and is able to produce verification metrics for you. So that's what we mean by the decoupled approach. It's sort of nothing different to what Tim explained in his slide sets, really. So why do we use E for our generation test bench? Well, obviously we had a lot of existing E code when from our sort of first generation test bench, but we decided to stick with SpecMini for our kind of generation test bench because it has a few, well, it's more than a few features that we quite liked. So one of them was this sort of aspect-orientated programming paradigm that you can use with E. So it allows you to kind of write your core constraints that may be specification derived in kind of, and it allows you to organize those in separate files. And then say you want to, create a test case for your generation test bench, which would produce a test that configures a particular feature, and that configures a particular feature. You can kind of you can put all that kind of code into one separate file that kind of cuts across all these constraints by kind of extending your core constraints. And in that test case, you're able to put kind of like control knobs to control your generation and biases for your constraints, and also any workarounds that your feature may have. That, for example, if your feature isn't quite mature yet. And we quite like this kind of this cross-cutting concerns feature in SpecMin. Also, SpecMin has strong debug tools that we quite like. It's very easy to step through the generation process and debug what's going wrong in your constraints. There's kind of three, let's say, I/O features in SpecMin that we use quite heavily when we are reading in, when we are both reading in pre-generated files and also outputting the configuration and expected data, etc., which is SpecMin tables, reflection API, and SpecMin's Python integration. So the SpecMin tables make it very easy to read in data from a file and treat that data as inside of a macro. So you can basically macro your constraints from an input file. And then the reflection API and the Python integration make it very easy to output the kind of the final state of your generated structures. So without having to hard code a lot of your generatable parameters, really. So your reflection API can look at your generated struct and output each of the fields, and your Python integration makes it easy to do a bit of post-processing to get it into the format that you would like. And yeah, I guess Tim touched on these kind of final 2 points. If you're able to read in pre-generated files, you can also read in pre-generated configurations and, check that those configurations are still valid if you do end up changing your constraints. And yeah, it's very, very easy to switch between kind of random generation and regenerating these old configurations, because you just essentially don't import your SpecMin table macros. And then yeah, if you're able to read in lots of pre-generated configurations, you can sort of you can get quite creative with this pre-generation. So we have a way of basically capturing the kind of the configurations that we would like to cover in a master file, which becomes the source for generating a black box coverage model, which is just saying, have I covered this configuration? Have I covered this configuration? And from that same master file, we're able to generate a set of partial configurations that would hit that black box coverage. And that not only helps you sort of close coverage quickly and deterministically, it helps you qualify that your generation test bench constraints are not being, you're not over constraining, because you'd kind of expect the configurations that are within your coverage model, you'd expect to be able to, generate those. You wouldn't expect any contradictions there. And with these kind of partial configurations, you're also able to kind of just soft constrain, the fields that are not of interest to maybe their default values. And these test cases instantly become nice kind of bring up test cases that you can give to the designers to debug, etc. Which can be, run alongside your normal random generation, your normal constrained random test cases. And we do this quite a lot in our team, actually. We find these partial configurations very, very useful. So just quickly to go over the benefits of the system Verilog simulation test bench. The reason we kind of shifted this code base from SpecMini to system Verilog really was there's a few reasons. But the main reason was it's slightly easier to find system Verilog human resources compared to SpecMini, because it is a much more popular language. People are more open to work with system Verilog. Also, there's no tie-in to any kind of particular simulator and vendor when you use system Verilog, and we had the option to use some emulation tools. However, that did come with a caveat that we had to adapt some test bench components to be able to support that. But they were the main reasons we changed to system Verilog in the simulation test bench. And it's pretty much a typical system Verilog UVM-based test bench, to be honest. The only subtle difference is that we're able to kind of use the expected data generated in our generation test bench. We're able to read that in and perform an end-to-end check, really. But yeah, it's set out in the exact same way that Tim drew his diagram in his presentation. We just have specialized drivers which are able to read in the files. There's no randomization in those drivers. They just read what's in the file and drive that to the design. So a few of the benefits is that, well, generation is much cheaper than simulation for us. It takes far less time to generate configurations, so you can actually afford to generate more configurations than you simulate and choose the best ones. And we use machine learning to choose the best ones, and we showed that, as Tim said, we showed that helped close coverage faster. You can also do some post-processing on your generated configurations to see how long they're going to run for, and you don't have to run your longer tests on the weekdays, for example. You can run them on weekends, or you can set simulation timeouts based on kind of how long you predict these tests to run. And storing your tests is also very useful, makes them very easy to search if you put them in an SQL database like we do. And you can write scripts to port tests to newer versions of your IP, or if there is a change to the registration specification, you can port these tests as well, and they become very good kind of starting tests for the next generation of your IPs. And bugs can bugs can be found more reliably. Well, they can be reproduced more reliably when you have a stored test case. If there's a delay between filing the bug and the person getting around to fixing the bug, the person trying to fix the bug would like to use their latest label to fix that bug rather than go back to an older label. And 99 times out of 100, they're able to sort of reproduce the same bug on the newer label. So a few enhancements we want to make is that using multiple workflows and sort of different tools can be slow to just sort of individually interactively run a test case, but we're working on sort of speeding that up. But it argued that this time is certainly made up elsewhere by reducing things like debugging invalid configurations, or certainly we think we make up that time elsewhere. And we're also working on sort of decoupling the generation and the simulation environments to an extent where we can use different kind of, we can sort of keep maybe the same generation environment across multiple derivatives and just change the simulation environment, for example. So yeah, that's my presentation. So happy to take any questions.
Brilliant. Okay, thanks, Reece. That's you've actually finished bang on time, so that means we don't have any time for questions, unfortunately. So maybe share with them, share those questions with you after the event. Okay, thank you. But thank you, Reece. It was very useful to see the actual application of this. So it's good to see Infineon actually what the results of this are. So thank you very much to yourself and to Tim. It's a combined presentation. I think it gives some very good food for thought in the way we do our generation and simulation. Thank you.